In 2014, astronomers using the Pan-STARRS survey spotted what looked, at first, like a plain, forgettable comet. A new designation, a long orbit, another icy drifter that would swing by the Sun and disappear for thousands of years. Its name was C2014S3, Pan-STARRS. But almost immediately, it started behaving in a way that made scientists do a double-take, because through the telescope, it didn't look like a normal comet at all. It looked like an asteroid, compact, sharp, and dry, with none of the dramatic fuzzy coma you'd expect from an icy body waking up near the Sun. And then, as it approached the inner solar system, it did the one thing that earned it its nickname. It showed a faint hint of activity, a whisper of dust, a barely there coma. The kind of subtle, I'm still alive signal that makes an inert-looking object suddenly feel uncanny. That's how C2014S3 became known in popular coverage as a zombie comet, something that looked dead until it didn't. And once you call something a zombie, people can't help themselves. The word carries a second implication: dormancy, reanimation, hidden processes, something that wakes up when conditions are right. It's a perfect metaphor for a comet. It's also a perfect trap, because it tempts you into an even bigger question. If it can look dead and then revive, could it be more than geology? Could it be, somehow, biological? Dead or dormant biological entity? That's the moment where the story becomes thrilling and dangerous at the same time, because the honest scientific answer is that there's no evidence C2014S3 is biological. But the reason this question keeps getting asked is worth exploring, because it exposes a deeper truth. Out at the edges of our observations, nature can look lifelike simply because it changes and responds. And C2014S3 is one of the cleanest examples of that illusion. To understand why, you need to understand what a normal comet is supposed to be. A typical long-period comet, especially one arriving from the distant reservoir known as the Oort cloud, is expected to be rich in ices. Water ice, carbon dioxide ice, carbon monoxide ice, and other frozen volatiles. Most of the time it lives in deep cold, far from the Sun. Then, when gravity nudges it inward, sunlight starts heating its surface. The ices sublimate, gas escapes, and that escaping gas drags dust with it, building a coma and sometimes a tail. The comet becomes visible not because it's a big solid body, but because it builds a temporary atmosphere that spreads out and reflects sunlight. That's the alive look of a comet: activity, outflow, change. An asteroid is the opposite image. Mostly rock, mostly inert, no coma, no tail. It reflects light like a solid object because it is one, no cloud, no outgassing show. C2014S3 sat awkwardly between those categories. Its orbit said comet. Its appearance said asteroid. And then it did just enough comet-like behavior to keep the argument burning. It produced a weak coma. Activity so faint you could miss it if you weren't looking carefully. That combination is exactly why scientists grouped it with a strange class of objects, sometimes nicknamed Manx comets, named after the Manx cat, famous for having little or no tail. The idea is simple. These are bodies on comet-like orbits that look unusually tailless, unusually asteroid-like, as if they're comets that lost their volatile life long ago, or rocky objects masquerading as comets because of where their orbits take them. So what is C2014S3? Here's the twist that makes it genuinely important. If it really originated in the Oort cloud, you'd expect it to be icy and active. But C2014S3 looked rocky, the kind of material we associate more with the inner solar system than the deep freeze outskirts. That suggests a wild possibility. It may have formed closer to the Sun, closer to where rocky planets form. and then been flung outward during the solar system's violent youth, stored in the Oort cloud like a fossil, and only now returned for a brief sunlit cameo. In other words, it might be a piece of the early inner solar system that got exiled to the outermost darkness and survived long enough to come back. That would make it a time capsule, not of biology, but of planet formation. So why does it show any activity at all? Because dead and dormant in comet science don't mean what they mean in horror movies. A comet can look dead for an extremely boring reason. Its surface can become sealed. Over time, as a comet repeatedly heats up near the sun, the easy-to-sublimate ices near the surface get depleted. Dust can build an insulating mantle. The surface becomes crusty, sealed, and less able to vent gas. The comet stops producing a dramatic coma and starts looking like a dark rock. That's what people mean by a dead or extinct comet. A dormant comet is similar, but with a key difference. The volatiles might still be there, just buried, hidden under a dust layer, locked beneath a crust, waiting for a crack, a landslide, a spin-up, or a fresh patch of exposed ice to let it out again. In that framework, a zombie comet is not supernatural. It's an object with a sealed body that occasionally exposes just enough volatile material to produce a faint burst of comet-like behavior. CDC 2014 S3's weak activity fits that story perfectly. It doesn't need biology. It doesn't even need a large amount of ice. It needs only a small amount of volatile material in the right place at the right time, plus sunlight. And that's why moves like life and acts alive metaphors are so sticky in space science, because we're watching systems respond. We're watching change. We're watching something that looks inert become active. But reaction is not life. Dry ice breathes too. So where does the biological angle come from? It comes from the same place it always comes from in space stories. Dormancy. Dormancy is a real biological strategy on Earth. Spores, cryptobiosis, seeds, microbes that shut down metabolism and wait. That makes people wonder whether something could travel through space asleep and wake up later. And there is a version of this idea that scientists discuss carefully. Panspermia, the hypothesis that life, or pre-life chemistry, could be transported between worlds. Not because a comet is alive, but because a comet could carry complex organics, or even shielded microbes, like a container. The problem is, the word could is doing a lot of work. Interplanetary transfer within a solar system is one thing. We know impacts can eject material off a planet, and we know rocks can travel between worlds. Interstellar transfer is far harsher. Over long timescales, space is not gentle. There's vacuum, extreme cold and heat cycling, and above all, radiation, UV and cosmic rays that damage complex molecules. A naked microbe on the surface would likely be sterilized. The only way biology stays plausible in transit is with shielding, buried under enough material to block radiation in a stable, dormant state for a long time. Could that happen in principle? People can argue about mechanisms. Did we see anything in C 2014 S3 that demands biology? No, nothing close. There were no measurements that looked like a biosignature, no chemical disequilibrium pattern, no isotopic ratios that scream biological processing, no complex suite of organics uniquely associated with metabolism, no sample return, no close-up imaging. We're not even in the same universe as proof. So if the title asks, dead or dormant biological entity? The responsible answer is neither. It's almost certainly a physical zombie, not a biological one. A rocky or rock-dominated body with minimal volatiles that can still produce weak comet-like activity. And that is still an incredible story, because it points to something that reshapes how we think about the solar system's earliest days. If objects like C2014S3 truly are rocky bodies stored in the Oort cloud, that implies the early solar system didn't just build planets in neat zones and leave them there. It implies chaos, gravitational scattering, giant planets migrating, material from the inner solar system being flung outward, and icy bodies being thrown inward. A messy mixing process that turned the Oort cloud into a deep-time archive, not just of icy comet material, but potentially of rocky, planet-forming debris. That matters because we can't time travel back to the first few million years when the planets were assembling. But we can find objects that formed then and have been refrigerated in deep space ever since. Every zombie comet, in this sense, is a survivor, an artifact from a period when the solar system was violent enough to throw pieces of itself into deep freeze. And there's one more reason C2014S3 is so valuable. It exposes how misleading our categories can be. We like binaries, comet or asteroid, alive or dead, rock or ice. But real objects don't care what we call them. They can be mixtures, they can evolve, they can wear masks, looking like one thing until the environment forces another behavior out of them. C2014S3 is a reminder that classification is often a story we tell after the physics has already happened. So what would it take to actually test any biological angle on something like this? It would take proximity, sampling, high-resolution spectroscopy of emitted gases and dust as it becomes active, and ideally, direct analysis of the particles in the coma. It would take the kind of detailed chemical work we can't reliably do from Earth on a faint object with a limited observing window. In other words, it would take what we almost never have when it comes to rare, dynamic visitors: time and access. And that's the real ending of the zombie comet story. Not that we found life, but that we found a new reason to build better readiness, better surveys to catch these objects early, and better missions that can intercept and analyze them up close. Because C2014S3 didn't arrive as an alien organism. It arrived as something more scientifically useful, a clue that the solar system's distant reservoirs may contain rocky relics we didn't expect. A body that looks dead until sunlight teases out the last of what it's hiding. A zombie, not because it's alive, but because it reminds us that in space, nothing is ever as simple as the labels we give it. And sometimes, the most important discoveries are the ones that force us to admit the categories were wrong.